it's going to be that, you know, U minus behave quite nicely on the support of matter measures. Okay. Or in other words, actually, we can say that, you know, not too precise, but we can say that, you know, in a shortcut, we can say that U minus is C11 on the support of matter measures. Okay, so that's going to be our goal. And this is matter called, this is a so-called the Lipschitz graph theorem. I mean, it's essentially what I just described. The proof is not too hard. I mean, we have, again, developed much of the tour to get to this point. But before I start, are there any questions or concerns or anything you would like to discuss first? Anything of your interest before the lecture? Okay, so if there's none, then let's start. I'll recall quickly what we have done very quickly on the left panel here. Again, we have the flow, the Euler-Lagrange flow. You know, we keep going with the keeping track of with the position and velocity. So it's a Lagrangian framework. You know, same in other aspect. When you say Lagrangian frameworks, that means you keep track with position and velocity. And you define a random probability measures to be flow invariance if you know, if you take integration on any test functions, it's the same under the flow. Okay, and again, I mean, let me recall the key thing that we have shown was that we have the minimization problem, mean of integral on Tn cross Rn of L xv d mu. Let's say mu is in the admissible set here. I'm just changing the notion a bit. And you have this minimization problem has a minimum value, which is minus C naught of 0. And the admissible set here is all probability measure mu. That is mu is invariant under the Euler-Lagrange flow. Okay, so that's the problem. And as I said, this was the thing set up by matter. People, you know, can deal with that, but there's one point that people said that this is a little bit restrictive, is that this condition, so this requirement is kind of nonlinear. Why is it nonlinear? It's nonlinear, it's hidden, right? You know, you require that it's to be invariant under the Euler-Lagrange flow. So there's an involvement of the Hamiltonian. But the Hamiltonian, you know, determines the Lagrangian, right? So you have a sort of a requirement that depending implicitly on the Lagrangian, and you are doing minimization problem with respect to the Lagrangian. So that's why the requirement is a little bit too strong. Later on, people can relax this requirement. But for now, that's a setup. Okay. Later on, Mane can relax it, introducing holonomy measures, and also by PD methods and other techniques. Now we can consider duality and relaxation. So the requirement of the admissible set is it's weaker. Okay, and non and it's linear, so it's not crazy. All right. So And we have already constructed minimizing measures, and each of the measures minimize the above formula is called matter measure. And again, the matter set is the closure of all support of matter measures, and the projected matter measure is just the projection on the torus. Okay. Uh, and one of the key things that we have observed the other day was that if you have xv is in a support of mu, a matter measure, then it turns out that you can run your your calibrated curves, so you can find a calibrated curve gamma mapping from R to the torus, not Rn, and you have gamma 0 equals to xv. So in this way, your calibrated curves is not just a ray, but it's the whole line. It's a line of geodesics, as you wish. And this is important because it allows us to, from the point xv, you can go either backward or forward in time. Okay. And this shows that, again, we have nice control. So last time we have shown that if this is the case, then u minus is differentiable at x, and furthermore you have the formula for the gradient. Du minus is dvl of xv. Okay, so that's really beautiful. And as I said, for today we're gonna dig deeper, right? We're gonna try to show that more or less, I mean, this is what people, it's exactly what that, but I can say that more or less, if xv is in the support of mu, a matter measure, then I would have that u is C11 at x. Okay, so that's sort of a very strong and important conclusion, telling me that I have better regularity, better probability at the point. Remember that, however, as I said, in 3 dimensions or higher, sometimes this is great, but it doesn't give us a lot of information because the matter measures can be tiny, can just sort of some curves on the entire plane, entire space. And, it's sort of like not too much, and it doesn't contain a lot of information. That's why, at this moment, understanding deeper probability in 3D or higher, pretty much open. And you can see also that in the proof, I can tell you right away, the technique is being repeated and being used quite regularly. So in other words, through this class, you can see that tours, not many. There are certain set of tours, and if you can grab those set of tours and keep those in your mind, then you're good to go. I mean, that's sort of the key point. And the tour that we are using here is same as if I have a point on the calibrated curves, interior of the calibrated curve, then it's differentiable. So what's the tour for this proof? The tour is the same. Is that again, from xv we can go backward and forward, right? That along the calibrated curve. And you can see actually hidden here, there's some interesting point I'll mention by the end of the class. So let me redraw again the picture that I just drew. So this is xv, which is gamma 0, gamma dot of 0. Okay, you have maybe let me write in a different way. So I'm only keeping track with gamma, right? It's hard to draw the whole curves. Gamma you know, gamma gamma dot. So this is gamma dot of v, which gamma dot 0 equals to v, and this is gamma 0 equals to x. So what I'm saying is that if I can go backward and forward in time, I can go either here, right? Backward in time, I can go forward in time. And I can, you know, keep track with the information backward and forward. And that helps me to essentially compare the values. You know, and that's exactly this theorem here. Again, depending on the context, you know, people, you see it later. This gonna imply that. So okay, I pick x to be a point on the matter set, projected matter set. Then for any vector h, I can compare the difference, right? You know, what's this called in numerics, the central difference. I forgot. I mean, this is the difference when you try to compute the second derivative in the h direction, right? So so what you have is that you can see, I mean, so roughly speaking here is that, you know, if you have xv is in the support of mu, a matter measure, then you know, the statement is equivalent to be like u minus of x plus h plus u minus of x minus h minus 2u minus x is less than or equals to c times h square. Okay, now let me sort of take advantage of the above picture. I'm just gonna, you know, like what I'm just gonna give you a sketch of the ideas, and then we go deeper into the proof. So what's the sketch of the idea? Well, you know, again, let me try to write this one in a better way. Well, I mean, I'm just gonna put this one to be x because otherwise it's gonna take a lot of space. So, you know, I have to compute the difference in the value, right? So maybe this is x plus h, this is x minus h. So how do I take advantage of the curve? And it's clear, right? You know, I have x plus h, x minus h, and I can go backward and forward in time along the calibrated curve. So that's a clear suggestion that, for example, if I'm going from gamma 0 to this is gamma 1, okay? Going forward along the characteristic, then I can try to compare the value between the 2 points, right? X plus h, x minus h, by bridging the thing, right? By sort of like connecting the dots from here to here and from there to there. So that's sort of gonna give me certain information going forward. Same gap, right? And similarly, I can also go backward to gamma minus 1 because I can go backward. And again, 1 and minus 1 are just some constants that I chose. You can choose different constant, doesn't matter. And if you go backward to gamma minus 1, you can do the same gap. You can bridge the points here, going backward. And you can compare the values. And by doing so, you have two-sided control. And essentially with those two-sided control, you are good to go. You're in good business. And that's sort of the key point. Okay, so you know, so this is sort of one of the very generic and beautiful idea in bridging the dynamics with the PDE is that you should consider the minimizing curves, geodesics, calibrated curves, backward characteristics, all indicate the same object. And along that, if you're at the end point, then it's hard to deduce anything. But if you're in the between, then the room that allows you to go backward and forward allows you to deduce information. And that's sort of the key. Okay, right. So let's do the proof. Okay, so that's exactly the picture I have drawn here. So, you know, so again, the earlier picture here, I drawn, you go back and forth. So here, let's start with just going forward in time. You're given you know, again, xv in the matter measures, and it's belong to certain support of certain measures, and you go forward in time. Okay, I'm using x here. Earlier I used c, sorry about that. Okay, so I'm using x, and um, maybe let me copy this picture here and maybe zoom it up a little bit. Okay, so this is better. So you can see that, you know, on the one hand, if I go along the calibrated curve, right, I would have u minus of x1 minus u minus of x0, which is x. It's just exactly uh, the equality, right, equals to the action functional. So Lx x dot ds plus c naught. Okay, again, one is just a constant that I chose. You can choose different constant. Um, 1/2, you know, 2 or something. All right. And then, you know, you would like to then, you know, again, this means that you have u minus of x. I hate the minus size. It's just occurring everywhere, but okay, let me try to respect the text. Um, so I'm just writing x0, which is exactly x, right? Just this one. Okay. Now I'm gonna try to construct the curves that, you know, connecting x minus h and x plus h to x1, right? So if I can do so, I should have, you know, for a part, I'm highlighting what's that part on the left panel now. I'm constructing a part going from x plus h to x1. And actually we have done this, right, earlier. What we are doing is that we are taking a linear combinations of the part x itself with a line segment connecting from h to 0, right? So, you know, when s is 0 is h, when s is 1 is 0. And when I'm connecting it that way, because the key thing is that I'm ending at the same endpoint x1, so I can use the fact that u minus is being dominated by L plus C naught to see that I also have, nope, I also have u minus of x1 minus u minus of x plus h is going to be less than equals to the integral along the part, right? You know, so that's the key thing that allows me to compare the values. Same, yeah, very beautiful. Okay, so if I write out the part, I have xs plus 1 minus sh. X those the sorry the velocity is just going to be x dot minus h ds plus c naught. Okay, so that's exactly the first thing, right? So you see that because of the endpoints are the same, when I do later on, when I compare the difference, the endpoint u minus of x1 go away. So, you know, that allows me to compare the values at x, x plus h, and x minus h. Okay. Now for the second one, I'm taking the part going from x minus h to x1. And that's exactly the same game. So it's just going to be xs minus 1 minus s times h. So that allows me to have u minus x1 minus u minus of x minus h is less than equals to integral from 0 to 1. Just the action, right? Minus. And what is important is that, you know, I'm using exactly the symmetry between minus h and h, right? So then when I write out the action functional, I need to respect that sort of symmetry so that later on I have good cancellation, right? I'm not going to make the two parts and not symmetry with respect to h, okay? So then from here you can see that it's clear that we can take the difference, right? if you take the difference, if I'm not mistaken, how do I do it? Yeah, I can take the first one, multiply by 2 and subtract the second one and third one. Then I would end up with, when I take, hold on. Yes, when I do the subtraction, then I have the u minus of x plus h plus u minus of x minus h minus 2 u minus of x is going to be greater than equals to just the action function, right? The c naught constant go away. So I would have integral from 0 to 1 2 L of x dot minus L x plus 1 minus sh x dot minus h minus L of x plus minus, let me put it down here, minus L of x minus 1 minus sh x dot plus h ds. Okay, so that's beautiful. You see that it's really, really important that I keep this symmetry here. Okay. Why? Because if I keep the symmetric property, then when I do the Taylor expansion, right, surely the zero order term goes away. The first order term cancel out, right? So that's why, you know, so this is just by Taylor expansion, by Taylor expansion. The zero order term goes away, and just allows me to conclude that only the no, zero and first order term goes away, only the second order term remains. So it's just going to be some c times h squared ds, which is going to be c times h squared. And clearly c here depends on constant depending on the square of L, right? Computing just on a ball, right? So in Tn, no. Infinity on Tn cross some ball, and surely depending on the speed of the of your calibrated curves, but that's also important. We have proved that our calibrated curves having bounded speed, and this one is exactly C here actually, maybe R if you wish. Okay, so that's really beautiful. It shows that we have control from below, right? And without the regularity of my calibrated curve, I'm not being able to deduce what I have. But because of, you know, the calibrated curves are having bounded velocity, everything is nice. The symmetric properties allow me to cancel the first order terms. That's why I'm only having x squared left. So that allows me to conclude the upper bound, a lower bound. So I have u minus of x plus h plus u minus of x minus h minus 2 u minus of x is greater than equal to minus c x squared h. Okay, so let me pause a little bit to see, are there any questions or concerns here? Is it clear? Good. Okay. Very good. All right. So I'm gonna ask us a question later, but yeah, maybe let me finish this proof, and then I'm gonna postpone a little bit for a question. Well, I mean the proof for the lower bound, no, upper bound is gonna be the same, right? So okay, so I'm gonna skip this part. I'm just gonna say that the proof of the upper bound is the same by using x minus 1. Okay, you know, again, for the upper bound, we are just going backward to x minus 1. We do exactly the same thing. We have those two inequalities here, you know, right? So that's the first one, and then I have also the second one. And what is remarkable is that when we go backward, then, you know, we can control, you know, u minus of x plus h and x minus h on the positive side, right? I mean, what I mean is that, you know, we take that subtracting u minus of x1. So then when we combine the things, we have exactly, you know, exactly this pattern that is less than equals to, you know, essentially the same thing. And then you can conclude that, you know, we have the upper bound. Again, very simple, but keep in your mind that this is one of the, you know, by far, after we have broken down all complicated aspects into simple matters, then this is by far one of the most important point that we have been using throughout, you know, matters and Manet and Fatty's ideas in dynamics, is that, you know, if you can go back and forth a little bit, then you can conclude those information. Okay, great. Right, so we are done with the theorem. So let's say that we are done with the theorem, saying that for x that sits in the projected matter set, then I would have u minus x plus h plus u minus of x minus h minus 2 u minus of x is less than or equal to c times h squared. And c here is independent of the choice of x, right? You have seen that c actually depends only on, this is exactly the constant c, depends exactly only on, you know, the what the velocity of the calibrated curves and the L infinity norm of the Hessian of L. Okay, all right. So now let me pause a little bit. I'm almost ready to prove the second result. Let me just say the second result, but I want to pause a little bit and tell you that actually there's some deeper thing hidden here. Okay, the second result is not too surprising. We can the proof is quite neat. There's certain beautiful cancellation, but you know, earlier we talked about the symmetric difference, and now we also have that, you know, instead of taking the dissymmetric difference, you're now proving exactly what I meant about the C11 over there, right? If you take u minus of x plus h minus u minus of x, subtracting the first order term, in the Taylor expansion, then it's bounded by c times h squared, right? And this is essentially the C11 claim. Okay, so we're gonna prove that. That's just gonna take us like 10 minutes. But before doing that, I have this following interesting remark. That is hidden in the above results. We can actually have, you know, some quite deep claims about some deep claims about differentiability of u minus. Okay, instead of taking points in the matter set, I'm just gonna taking points on our backward characteristics or calibrated curves, okay? So let's see. I'm gonna start at the point gamma 0 equals to x. I'm gonna go along the backward characteristics. Okay, so gamma mapping from minus infinity to 0 to the Tn is a calibrated curve, or is a backward characteristic with gamma 0 equals to x. Again, this is much how to put it, a much bigger set compared to the matter sets, right? As I said, for points belong to the matter sets, it has to satisfy further requirements. But for calibrated curves or backward characteristic, for any point we can find such a calibrated curves or backward characteristic, right? And what I'm claiming now is this point. Now if I take y to be gamma of t for t less than 0, right? Then I claim that hidden in the above proof, we actually have quite nice control at y, right? Earlier we have shown that u minus is differentiable at y, sure. At y, okay? But now I claim that we have better, further. U minus is also C11 at y. So this is really, really a better claim, because it tells us that, in fact, like if you go along all the backward characteristics for all points, inside those backward characteristics, U is sort of C11 there, right? That's amazing. However, that's a catch. The C11, the constant might depend on the position Y, okay? And this is clear. Okay, how do we see this? Okay, so let me just draw a picture and you see. So I have gamma 0 equals to x. If you start at a point y equals to gamma t here, the same thing happens, right? You can actually repeat the same proof. You can go forward in time and backward in time along the calibrated curve. Going backward is totally fine, because you can go as far as you want, okay? So going backward from y equals to gamma t is totally fine. As we can go again to anything that you want, right? For example, you can go to z, which is gamma t minus 1, okay? And repeat exactly the same proof earlier. If you require, or if you look back to the same proof earlier, you have the second claim. So you can go backward in time always. So let me just copy that. Then you have uy plus h minus 2 plus uy minus h minus 2uy is always less than or equal to c times h squared for all h in Rn, or the torus, doesn't matter, and c here is independent of the choice of y. Okay, so if you think a little bit further, you can infer that this is actually implying that u is semi concave, right? Meaning that if you're subtracting something, subtracting a quadratic polynomial, then it's becoming a concave function. Beautiful. That's amazing. And actually what I'm saying here is also correct for x, the you know, it's even correct for the point x, which is the end of the array, right? Because for the end of the array you can always go backward. Okay, so that's great. Now going forward, we don't have that. So going forward from y, you know, if t is less than -1, sure, you can go forward in an amount of time t, but in general, you can only go forward for a short amount of time, right? So we can only go forward for a short amount of time. Say, okay, let's I'm running out of characters on notions, say tau. Okay, I can go forward for a short amount of time, say tau equals to t over 2. Okay, and tau might be small, right? So now if you repeat the same proof, let's go back to this proof earlier. The first claim, right? You're going forward in time, everything looks perfectly nice. What's the difference? The difference is only when you try to connect the parts. What I'm highlighting here, what I'm putting the box on the left panel here. If you connect the parts, you only have an amount of time tau to go from 0 to h and stuff like that, right? So so again, it's just a technical point, but you can see that, okay, let me just say that if you go from say from x, oops, what's that? I don't know what happened. You go from x plus h to the next point, which is gamma of t plus tau, right? Then what do? Then you just look at your part that's going from, it's just going to be gamma s, and you have to connect from h to 0 in an amount of time tau. So if I'm not mistaken, you take 1 minus s over tau times h. This is for t less than equals to s less than equals to t plus tau. No, this is not 1 minus s. Yeah, I take it back. No, give me 1 second. Not 1 minus s, but what? It should be s minus t over tau. No, I'm sorry. T plus tau minus s over tau times h. Okay, that's fine. Again, there's only a tiny difference is that I have to divide everything by tau, and tau can be tiny, right? So you're gonna have the Lagrangian to be of the sort, like integral from t to t plus tau of L of gamma s t plus tau minus s over tau h, and the velocity is going to be gamma dot of s. And you differentiate in s, you're going to have minus 1 over tau times h, stuff like that, right? So when you compare the difference, you know, the 1 over tau is going to come into the game. And if I'm not mistaken, you can only deduce that u of minus u minus of y plus h plus u minus of y minus h minus 2 u minus of y. This is going to be greater than or equals to some minus constant c, maybe over tau square or something like that, times h, something like that. Okay, so you see that the upper bound is totally fine, but the lower bound depending on the position of y. So essentially, this result is really deep. It tells us that if you go back along the backward characteristics, your function is essentially locally C11, going back except the endpoints. Okay, so that is great, and this is not surprising because you can see that I have shown here that you have U is semi-concave. Okay, semi-concave means that if you add or subtract a quadratic term, it becomes concave, right? But for a convex or concave function, by Alexandrov theorem, you have that your function is almost everywhere twice differentiable. And this is exactly that. Okay, so you see that I have the upper bounds always true, the lower bound is local, but it tells me that except the endpoints, which might give me a set of measure 0, but except those points, it's almost everywhere twice differentiable. Amazing and beautiful. Okay. Of course, what I meant here is that we can prove it directly without using the Alexandrov theorem, because U minus is not any function is satisfying our PDE. So we have such a great claim. Maybe I can say, so this is a corollary that U minus is almost everywhere twice differentiable. And also that U minus, I mean, I should switch the order, but fine, is semi-concave. Okay, it's hidden here. Any question or concern here? Is it clear? Okay, great. So, the problem is that really that we cannot control the endpoints. Like at the endpoint X, we don't know at which point that is differential, at which point it's not, and stuff like that. And that's why it's complicated. Anyway, all right, so let me just do quickly the proof now that is showing clearly is C11. But you can exactly repeat what we have done, right? What we have done is that we are just carefully recalling the first part, that to control U minus of X plus H minus U minus of X from the below, you just plug in what you have, right? So you're just comparing this L with this L. So just the difference in value. And I'm not using anything spectacular here. I'm just using again the Taylor expansion. Okay, I'm talking too much, so I forgot. So it's just a Taylor expansion. And the Taylor expansion, when you compare the difference in X, you're gonna have dxl occurs, right? Multiply with the difference. That's exactly that. And you compare the difference in V, right? So difference in V is gonna be dVL. Multiply with the difference, which is exactly H, right? Not a big deal here. And there's an error terms. That's the second order term. I mean, yes. So C minus H squared. And here there's a neat trick here that we are using the Euler Lagrange equation, right? I mean, we have used this one once. And to use the Euler Lagrange equation, I realized that dx of L is d over ds of dv of L. Okay, so this is an Euler Lagrange equation. This equals to that. And then I realized that so this is from Euler Lagrange. Okay, and then the next step is that I realized that the sum of the two is just exactly the dot product of the the product rule. So it's just d over ds of this term, right? If you see, you hit the derivative on dv, you have the first term, right? You hit the derivative on s minus 1, you get 1, right? So we have the second term. That's it. So So that's a neat trick by always using Euler Lagrange and, you know, switch it back and forth. So you have now the fundamental theorem in calculus. You are just integrating this term in ds. And you realize that when s equals to 1, it goes away, right? So what remains is only when s equal to 0, okay? And when s equal to 0, you have exactly this term. It's really beautiful. And this term is nothing but du minus of h. Okay, so we are done. Again, again, it gives us one bound and you use the other thing to get the second bound. Again, what is really remarkable for me is that in this chain of equalities or inequalities together with equality, we use neatly the Euler-Lagrange equation. We use neatly the combination of them gives me a whole derivative. And then we use also neatly the fact that we have computed du minus of x is dvl of xv. So every step is simple, but we have actually, you know, used everything we have developed before. So this is quite a rare class that everything that we have developed come into play. It constitutes of a whole body. That's why, you know, it's not like I have done with one topic and I go away and I'm introducing to you another topic, but here everything is twisted and convoluted and involved. So every piece of it is simple, but when you have this whole body, like if you see this whole result alone, that is remarkable. Okay. Yeah, and so I'm done. So I have time for questions or concerns. So I mean, I talk to people from both dynamics and PDE. From the viewpoint of people from dynamical system like Fatih and others, at this moment it's quite hard to go forward. There are a lot of new papers sort of saying like Wickham theory for this, Wickham theory for that. So they are trying to do kind of Wickham theory for different models, and essentially proving this kind of Wickham theorem and proving the existence of backward characteristics of calibrated curves. You can go to the archive. I think that there have been recent papers quite recently, like last week or so, on this same aspect. But that's sort of just constructing the analogs of this thing for different objects. Those are not easy. I'm just saying that, you know, like you have the same framework. To do those for those models or new models or things that can be really challenging technicalities that one has to overcome. But for the core Wickham theory, there are a lot of questions that I have like discussed with you that need new ideas and tools, and those are totally open. So that's from the dynamical viewpoint. Now from the PD viewpoint, from my view, or you know, people like, as I said, you know, Yifeng Yu or EC or Diego Gomez or Evans, the viewpoint from PD is that Wickham theory is quite neat. It gives us certain tools and certain new ideas, you know, like what I'm describing to you here. This is by no means available in just doing well-postness from PD viewpoint, right? If you don't go deeply into those minimizing curves and understanding them. So in a way, Wickham theory gives you a good set of tools and maybe a good certain good principle. So principles, you know, okay, if you have this point, you can go back and forth and you can sort of like do certain analysis and get deeper result. But clearly it lacks, you know, really that big further developments to, you know, to advance, to understand deeper the theory itself. However, I mean, this is good for PD, right? Because you can use those ideas and handle various different problems. You have an added set of tools and added layers of understanding of the solutions, and you know, there's always a trade-off. Okay. Other questions or concerns? Anything you would like to discuss for today? Okay, so I guess that, you know, similarly that today is quite clear. Again, you have seen this kind of trick and ideas have been happening a few times, and I'm, you know, I'm a mathematician, so I'm quite convinced that once I have told you a multiple number of times, and it becoming standard for you. You know, it's sort of like we are getting used to it. Myself as well, I'm getting used to it. So that's pretty much it. And you know, again, later on, who knows, right? You know, for your kind of problems, you have, you know, you have developed this kind of ideas in your mind, so you can you know, you can use it as some good tools later on. All right, so great. Other than that, then again, stay safe and healthy. Vaccines are available, hopefully for some of us, or for some of you, if you have chance, then consider it. And I'll see you on Wednesday. After that, we have a good little break. Okay, thank you all. Bye for now.